Welcome. In this video, we are going to discuss the uniform distribution. Before starting uniform distributions, till now what we have done is the discrete distributions. From now onwards, we are moving to continuous distributions. Okay, this uniform distribution. When do we make use of this uniform distribution? You can use this even in the case of discrete. You may wonder, what am I telling right now, right? Because uniform distribution means in the set of possible outcomes, that is what we call it as sample space. Okay, in a sample space, every element or every entry in the sample space has a equal chance. Okay, that is what we model under uniform distribution. Here if you see, the density function, we are modeling it as a continuous distribution. So random variable is said to be uniform in a particular interval if the PDF is given in this form. Now you can very well think, can it be defined on some infinite interval? Is it possible? Suppose you wish to define it on this interval. Is this possible? If you look at the definition, your f of x has to be 1 upon b minus a. So it is 1 upon infinity. This is not possible. So whenever we are defining something in uniform distribution, it is defined on some discrete sample space or interval of finite length. Okay. Now given we have a problem. Before going to the problem, let us try to derive the mean and variance of this uniform distribution. Suppose if you are trying to find out the moment generating function, it is what? This is expectation of e to the power tx. Here it is defined from a to b, right? E to the power dx multiplied with 1 upon b minus a dx. So this 1 upon b minus a is a constant that we take outside. Okay, the derivative of e to the power tx is e to the power tx divided by t, and it is over the limit a to b. Okay, when we substitute it, what will we get? Okay, anyway this t is independent of x, so we shall take the t outside, b minus a times of t, and this would be e to the power tb minus e to the power ta. Okay, this is the moment generating function of this distribution. Now if you have to find the mean out of it and variance out of it, now that you can very well observe that t is present both in the numerator and in the denominator. If you want to differentiate it and perform the calculations, you are free to do it. Now let me try to derive the mean using the usual sense. That is what? Expectation of x. It is integral a to b x multiplied with the density function. Okay, so 1 upon b minus a is a constant outside, so it is x square upon 2. It is from a to b. So what am I going to get? It is 1 upon b minus a multiplied with b square upon 2 minus a square upon 2. So let me take this 2 as a common quantity multiplied with b minus a, and this is b square minus a square. So this shall be written as b plus a into b minus a divided by 2 times of b minus a. So this gets cancelled. Remember, whenever we talk about some open interval, this a and b are different quantities. So this is some positive quantity. So this cancellation is valid. So the mean is b plus a upon 2. Supposing we are looking to find out the variance. So integral a to b x square 1 upon b minus a dx. So this 1 upon b minus a, let us take outside. So it is x cube upon 3 over the limit a to b, isn't it? So it is 1 upon 3 times of b minus a, b cube minus a cube, right? Okay, If you just expand it, it would be b minus a multiplied with b square plus ab plus a square upon 3 times of b minus a, and this b minus a gets cancelled. It is b square plus ab plus a square upon 3. Now that it is expectation of x square, now we need variance of x. It is what? Expectation of x square minus mu square, isn't it? It is b square plus ab plus a square upon 3 minus b plus a upon 2 whole square, right? So you will get this as some b square plus ab plus a square minus times of, okay, this is upon 3, b square plus 2ab plus a square upon 4, right? We'll have to take the LCM, so it would be 4b square plus 4ab plus 4a square minus 3b square minus 6ab minus 3a square upon 12. So finally what we are going to have is b square minus 2ab plus a square upon 12, that is b minus a whole square upon 12. This is our variance. Okay, so as whatever we have done till now is mu is a plus b upon 2 or b plus a upon 2, and sigma square is b minus a whole square upon 12. Okay, now coming back to the problem that we have here, assume that the error made in the measurement is a uniform random variable in this interval. Okay, what is the probability that in a measurement the error lies in this interval? Okay, for this situation, first of all, let us try to write the density function. Okay, that I am writing in green color, hope you can see it. So it is 1 minus b, it is 0.15 minus of this a, that is minus 0.15. So it is 1 upon 0.3. Okay, this is valid in this interval. Now we are asked to find out the probability that it is x is lying in minus 0.1 to 0.1. So all you have to do is to integrate it from minus 0.1 to 0.1 to this function, that is this one. So this is a constant, so we take it outside. Okay, when we integrate it, we would get 0.1 minus of minus 0.1. So it is 0.2 upon 0.3, which is 2 by 3. This is the required probability. Okay. Moving further, we have a problem here. Here it is said that average daily procurement of fresh milk produces union is 40,000 liters, which means their mean value is, that is mean, a plus b upon 2, this value is 40,000, that is given, and the minimum quantity is 25 liters per day. Assuming uniform distribution, we will have to find out the maximum milk procurement and the probability that the procurement will exceed 35 liters. Okay, first of all, let us try to find out the maximum. If you come back to the density function of this one, this A is the minimum possibility and B is the maximum possibility. So with that in our mind, this is the mean value 40,000 and A is given to be 25,000. Okay, and we need to find out the B value. If we substitute this mu equals 40,000 and A equals 25,000 in this mean formula, what will we have is, that is 40,000 will be equated to 25,000 plus some quantity divided by 2. So from this our B is what? It is 80,000 minus 25,000 and that happens to be the 55,000. isn't it? Okay. Now we are asked to find out the probability that it is exceeding 35 liters. Okay, so from 35 to certain thing we'll have to find out, whereas in uniform distribution it is defined in some finite interval. Therefore the maximum that we have found, that is 55,000, so it cannot exceed 55,000. We have that one. Okay, now how did we get these stuff? It is the probability of this one. So this is given as integral from 35,000 to 55,000. Okay, 1 divided by 55 minus 55,000 minus 25,000, isn't it? If we just substitute in the density function, this is what we are going to have. So when we integrate it, we would get 55,000 minus 35,000 upon 55 minus 25. Okay, when you make the calculation and simplify it, this is what you are getting. So it means this is the probability that the procurement is exceeding 35 liters. That's it. Thank you.